Hello, how's it going? In this video, I'm going to look at the scale transformation. In general, our transformations, matrix transformations, will be 4x4 with, I said 4x4, with the system x, y, z, and 1. Now, it just so turns out that the final row of the matrix will be the identity row, because after applying a transformation, we always want to keep a value of 1 in the w coordinate. That's the one beyond z. Okay. So, how does the scale transform work? Well, let's go with no, I won't do that yet. Let's just do a simple case. Let's say I want to scale by some factor in the x, the y, and the z. This matrix here, this form, is the scale transform. Let's work this out by computing the multiplication. So we take the first row through the first column, and that is the first row, first column of the outputs. We have the scale factor times x, and then plus 0 times y, plus 0 times z, plus 0 times 1. So that's the only change that has occurred. The x value has multiplied by that scale factor multiplier. Then for the second row, first column, we have 0 times x, okay, no difference. Scale factor y times the y coordinate plus 0 times z plus 0 times 1. And likewise, so 0 times x, 0 times y, scale factor for z, and 0 times 1, and then 0, 0, 0, and 1 times 1. So remember, we always keep 1 in the w coordinate. Okay, that's all well and good. Well, how do we deal with sets of points? No problem. Each column is a point that will undergo this transformation. So let's say, for instance, we'll go with a really simple example of, let's go 2, 3, 4. So the x factor is 2, the y factor is 3, z factor is 4. Okay, and let's transform a set of points. Let's start with 1, 1, 1. Okay, and so remember, the 1 in the w coordinate is artificial, and so really the points are 1, 1, 1, 2, 8, negative 4, and 3, negative 3, 1. And it really doesn't matter. We could use decimals. It works the same way. So we take it step by step. So we take the first column, first row, first column, 2 plus 0 plus 0 plus 0. Okay. Second row, first column, 0 plus 3 plus 0 plus 0. Okay, great. And 0 plus 0 plus 4 plus 0, 0, 0, 0, 1. Okay, awesome. Then we have a look at the second column, which represents the second point which we're transforming. So we have 2 times 2, that's 4, 0, 0, 0, 0, 24, 0, 0, 0, 0, negative 16, 0, and so on. So we can see that the scale transform is acting like we expect it to. It is multiplying the x, y, or z coordinate by the given x, y, or z factor. So just for completeness, we can finish this off. We have 6, negative 9, and 4. And that 1 in the end always stays there, no matter what. Okay, so that's all well and good. On paper, how do we implement this in code? So there's sort of two ways to transform vertices. One way is to apply a matrix transform by hand on the raw data and then sort of flash that data over to the graphics card. And the other way is to use a uniform vector, a uniform matrix. I want to look at doing it by hand first because that's a little more informative. So we can leave the details of this app for now. It's basically just describing a scale factor. But here, if we want to, in the language of transformations, we have what's called object data and image data. The object data always exists in memory. Then a transform, and that copy of that data is taken, a transform is applied, and that produces what we call image data. This makes sure that, for instance, if we rotate a shape around, the shape is not continually rotating because we always refer back to the original data when we apply a transform. Used to get myself in trouble with that a lot. So the way this is set up at the moment, we have the X coordinate, Y, Z, and then always 1 on the end. So this is pretty much the same as the diagram I just wrote, except transposed, but it works the same way. So we have this data, and then what we're doing is just casting it into a matrix, and we'll see what this actually looks like in a second. But what we really want to focus on is this function here, build vertices. So I'll just close the rest down. If we go to the app, in the initializer, what I'm doing is I'm making a triangle which has a scale factor of 0.3 in the X, 0.6 in the Y, 0.9 in the Z. Then I'm applying that transformation to the shape. So let me just run this. So we can see that in fact it has been, if we go back, up here. Okay, so we have, let's bring that up again. We can see here the original positions are -1 in the X, -1 in the Y, which is this red corner, bottom left. Then we apply a transformation factor of 0.3 in the X, 0.6 in the Y. And so that becomes -0.3, -0.6. As we can see here, it sort of shrinks, and it shrinks a lot more in the X than the Y. So yeah, we can look through this code and see that we have our positions, we apply this transform, and then the result is pretty much what we expect. Now, how do we do this in the code? Well, our data has been shifted into 3x4, so 3 rows, 4 columns. I know this is a transpose of what we were working with before, because if each column is a point, then it would be the transpose of that. But this is just the way that NumPy works. It's the same concept. So what we do is we call this matrix multiply. We multiply the original positions by the transform, and that produces the set. That produces a set of transformed points. And then we just sort of loop through, take the X, Y, Z, so excluding the W coordinate, and just zip it all together. Now, I know I'm sort of speaking on this probably more than it has to be. I mean, the topic was mathematical transforms, but this is the code. And yeah, why not? I will include that code in the GitHub repo if you want to have more of a look at it. But this is good for understanding things. Obviously, there are some issues. If we have a matrix, a vector, vertices with heaps and heaps of points, 1,000 points, we can't be doing that on the CPU. Even if we're using NumPy, that's not the efficient way to do it. So the other example works almost the same way. And here we are taking in a matrix in the vertex shader and applying that straight away. So the GPU is doing the multiplication for us, which is fine. GPUs are very good at doing matrix multiplication. So just like I was saying, this goes almost exactly the same way as the previous code. The difference is we define the vertices straight away as a flat matrix. We don't worry about reshaping it. We send that data over straight away. We keep that there. We don't touch it again. And then in the main loop, we use this. This is actually the same matrix as I did in the previous code section. We have this create from scale function, takes in the scale here, the triangle scale, and then we just send that over to the shader and it does its thing. So yeah, there we have it. An example of a scale transform, mathematically how it works, and in code how we implement it. I hope this is useful, and yeah, I'll see you again soon. Bye.